When we think of the Great Pyramid of Giza today, most of us picture a weathered, stepped pyramid, a colossal structure rising from the sands of Egypt, with rough stones forming a layered, almost stair-like surface. But this was not how the pyramid looked when it was first completed. For thousands of years after its construction, around 2560 BC, it stood as something quite different, a smooth, gleaming monument covered in polished white limestone, known as casing stones. These stones were cut with such precision that the pyramid's faces were perfectly flat and reflective, giving it an almost otherworldly brilliance. Imagine standing at a distance and seeing the pyramid shimmering in the desert sun, its surface so smooth and reflective that it was said to resemble a radiant jewel, a dazzling white mountain visible for miles. This casing created a smooth, angled surface that covered the entire structure from base to apex, transforming the pyramid into a unified, shining beacon. Yet, most of these stones are gone. Their absence leaves the inner core of rougher stones exposed, which gives the pyramid the stepped appearance we see today. And this raises the obvious question: what happened to the casing stones? How did this symbol of perfection become the weathered, stripped pyramid that we now know? For centuries, the prevailing explanation has been fairly straightforward. The casing stones were removed, either by natural disaster or human activity, over time. According to this theory, the most significant event in the loss of the casing stones occurred in 1303 AD, when a major earthquake hit the region. This earthquake allegedly loosened the outer casing stones, making them vulnerable to damage and displacement. It's suggested that after the earthquake, the stones fell to the ground, and then over the next few centuries, local builders repurposed these fallen stones to construct other monumental structures in Cairo, such as the Cairo Citadel and the Sultan Hassan Mosque. To understand this better, let's break down the traditional explanation into two components: natural disaster and human quarrying. The natural disaster theory suggests that the earthquake of 1303 caused the casing stones to shift and detach from the pyramid. It's argued that the force of the quake, felt across the eastern Mediterranean, was strong enough to dislodge the stones from their originally perfect alignment, leaving many either precariously loose or outright destroyed. The quarrying explanation posits that once these stones were loosened, they became easy pickings for human activity. Builders of medieval Cairo saw an opportunity. Rather than quarry new limestone from far-off sites, they could simply take the fallen casing stones from Giza and use them to construct their own buildings. This practice of reusing materials was common throughout history, so it's not hard to imagine that this might have happened to some extent. But as compelling as these explanations might sound, they leave us with some puzzling questions. For instance, why are the casing stones missing predominantly from the middle section of the pyramid, while the stones at the base and the very top are still intact? If an earthquake was powerful enough to dislodge the casing stones, why didn't it affect the pyramid uniformly? And if quarrying was the main factor, why would builders bypass the easier-to-reach stones at the base and instead focus on those in the middle? More importantly, there's a surprising lack of evidence for earthquake damage. The core stones that remain exposed in the middle section show little to no displacement or cracking that we'd expect to see if the earthquake had been strong enough to strip the pyramid of its casing. And while it's true that some casing stones were repurposed for use in Cairo, this doesn't explain why they fell off in the first place. So this begs the question: is there another explanation that better accounts for the selective loss of casing stones, their distribution, and the overall structural integrity of the pyramid? Let's consider an alternative theory, one that ties together not just the missing casing stones, but also the remarkable electromagnetic properties of the pyramid, its unique design, and even the ancient Egyptians' own accounts of solar activity. What if the missing casing stones were the result of a cosmic event, not just an earthquake or quarrying? Imagine a world where, thousands of years ago, the Great Pyramid interacted with forces from beyond our planet, forces like a solar flare or a coronal mass ejection, CME, from the sun. The polished Tura limestone casing stones, acting as a conductive outer layer, could have been affected by a massive burst of electrical energy induced by a solar event. This kind of discharge would not affect the whole pyramid uniformly, as an earthquake might. Instead, it would selectively interact with the pyramid's most conductive surfaces, the polished stones in the middle section, dislodging and blowing them off, while leaving other parts of the structure relatively untouched. This is not a wild fantasy, but an idea grounded in modern scientific observations and ancient accounts. The pyramid itself shows electromagnetic anomalies. It's not just an inert pile of stones. And the Egyptians were intensely focused on solar phenomena, with deities like Ra, the sun god, representing cosmic power that could be both life-giving and destructive. So let's take a journey into the evidence, into the electromagnetic properties of the pyramid, the physical condition of the remaining stones, and the scientific possibilities of how a massive solar event could have selectively stripped away the pyramid's casing, leaving behind the mystery we see today. In doing so, we'll weave together archaeology, geology, physics, and mythology to paint a picture of the pyramid that's not just a remnant of an ancient past, but a monument that has interacted with the very forces of the cosmos. With this alternative theory in mind, let's delve deeper into the details, exploring the evidence of electromagnetic anomalies, the historical and geological records of catastrophic solar events, the patterns of casing stone loss, and the triadic analysis of the pyramid's structure. By the end, we'll see how all these elements fit together to support a new and perhaps more compelling explanation for the Great Pyramid's missing casing stones. Let's start by diving into the pyramid's geometry and materials. The structure itself has long been a subject of fascination, not only for its architectural brilliance but also for its potential electromagnetic properties. Several studies have measured electromagnetic anomalies around pyramid sites, with the Great Pyramid standing out as a conductor of sorts. Imagine a massive geometric form that not only looks imposing, but also interacts with the Earth's electromagnetic field. These anomalies appear to concentrate around certain areas of the pyramid, particularly around the midsection, where the bulk of the missing casing stones were once located. Why is this significant? Consider that these polished casing stones were made of Tura limestone, a material known to have unique conductive properties, particularly when polished to a smooth finish. Unlike the rough core stones of the pyramid, which were porous and had limited conductive capacity, the polished outer casing could efficiently conduct electrical currents. When we examine the pyramid's structure from an electromagnetic perspective, it becomes more than a tomb. It may have been a structure designed to channel, focus, or interact with the Earth's natural energies. This brings us to the properties of Tura limestone. Studies have shown that this type of limestone, especially in its polished form, is far more conductive than the rougher stones used in the core of the pyramid. The smooth, reflective surface may have allowed for an interaction with external electrical currents, making the casing stones far more vulnerable to electrical phenomena than the core stones beneath them. If a large-scale solar event were to occur, the polished outer surface would have become the focal point of any electrical discharge, causing the detachment of the middle stones while leaving the top and bottom relatively unaffected. This selective conductivity aligns with the current pattern of missing stones, offering a new lens through which to understand their disappearance. We don't just rely on the physical evidence of the pyramid's materials, we must also look to historical and mythological records. Ancient Egypt had a deep reverence for the sun, seen in the worship of deities like Ra and Sekhmet. Stories of the Eye of Ra, which could unleash catastrophic force, and accounts of Sekhmet's destructive power, hint at events where the sun played an active and sometimes dangerous role in daily life. What if these mythological references were based on real events? Events that shaped not just their culture but their environment. Some researchers have suggested that these texts may describe atmospheric or solar phenomena, perhaps a solar flare or coronal mass ejection, CME, that could have triggered large-scale electrical events on Earth. If such an event happened, the pyramid, with its conductive casing stones, might have interacted with this surge in solar energy, leading to an electrical discharge strong enough to blow off its middle layer of casing stones. To build on this theory, we can look at geomagnetic evidence from ice cores, tree rings, and radiocarbon dating. Scientific research has identified periods of heightened solar activity throughout history. These periods are marked by spikes in isotopic anomalies like carbon-14, which suggest increased cosmic radiation reaching the Earth's surface. If one of these periods aligns with the proposed timeline of the casing stone's removal, it would lend significant weight to the hypothesis that a solar event caused the damage to the pyramid. Imagine being able to pinpoint a solar flare or coronal mass ejection in the historical record, mapping it directly to the time when the pyramid lost its smooth outer surface. This would not only reinforce the idea of the pyramid as a structure capable of interacting with the Earth's natural energies, but also provide a tangible link between ancient construction and cosmic events. Now let's talk about the physical evidence on the pyramid itself. The pattern of missing versus remaining casing stones is not random, it's highly selective. Most of the missing stones come from the middle section of the pyramid, while stones remain at the base and apex. If we map this pattern in detail, we can start to see how an electrical discharge might have behaved. Electrical discharges tend to move along paths of least resistance, targeting the most conductive surfaces, which in this case would be the polished limestone casing. The middle of the pyramid, being farthest from the grounding effect of the Earth and most exposed to the open sky, would have experienced the highest concentration of electrical energy. This helps explain why the stones in the middle are missing while the apex and base remain largely intact. It suggests a targeted force, not a uniform one like an earthquake. If quarrying were responsible, we would expect a more gradual removal from the base upward, not this middle first pattern. The stones that do remain, particularly at the base and apex, present an opportunity for deeper analysis. If we were to examine them microscopically, we might find evidence of thermal damage or electrical stress, signs of high-energy plasma or electrical arcing. This could manifest as pitting, melting, or vitrification that would be distinct from the effects of mechanical quarrying. Additionally, any conductive residues or fractures caused by electrical stress would be critical in distinguishing between natural weathering, human intervention, and an electrical event. Now, let's look at the pyramid through the lens of a triadic structure: missing casing stones, remaining casing stones, and understructure stones. This categorization allows us to explore how each part of the pyramid reacted differently to various forces. First, consider the missing casing stones, which were mainly located in the middle section. The middle was likely the most exposed to an electrical event because it was farthest from the grounding effect of the Earth and most vulnerable to electrical concentration. The base of the pyramid acts as a grounding point. Electricity naturally moves toward the ground, so the base casing stones would have been less affected by any discharge. At the same time, the apex of the pyramid, being pointed and isolated, would have efficiently channeled electrical charge away, sparing it from the brunt of the damage that affected the middle. The understructure stones, the rough limestone blocks making up the bulk of the pyramid, are non-conductive. They were shielded beneath the casing stones, and as a result, they were unaffected by the electrical discharge. Their current state of preservation suggests that whatever force removed the casing stones did not penetrate deeply into the structure, reinforcing the idea that the damage was surface level and related to the outer conductive layer. Scientific models of plasma and electrical discharge. How can we test this theory? Through laboratory simulations. Experiments that replicate electrical discharges on limestone can provide a physical model for how the pyramid might have been affected. Plasma research shows that electrical discharges tend to interact with conductive surfaces in specific ways, causing effects like pitting, melting, and displacement of material. Recreating these conditions in a controlled setting with Tura limestone would visually and physically demonstrate how a solar-induced electrical event might have stripped away the pyramid's casing stones. This theory doesn't just stand alone at Giza. To validate it, we should look at other ancient structures built with similar materials. Are there signs of selective stone loss or evidence of high energy damage on these monuments as well? If so, this would provide a precedent and contextualize the solar discharge hypothesis as part of a wider pattern of ancient structures interacting with the Earth's electromagnetic field. What we see today when we look at the Great Pyramid is not just a bare monument, it's a witness to the forces of the Earth and sky, shaped by both human hands and cosmic energies. The theory of a solar-induced electrical discharge offers a new perspective on this ancient structure, connecting its construction materials, electromagnetic properties, and pattern of damage in a way that challenges our understanding of its past. By examining the missing stones, analyzing the remaining stones, and considering the pyramid as a triadic structure, we open up the possibility that this monumental edifice was more than just a tomb. It was an active participant in the cosmic interplay between Earth and Sun. The pyramid's transformation is not simply the result of quarrying or natural disaster. It might well be the story of an ancient structure interacting with forces far greater than itself, forces we are only beginning to understand. But before we wrap up, let's address two final critical points that further strengthen this alternative theory. First, let's consider the sheer effort involved in removing those casing stones for reuse. We know that polished Tura limestone stones were highly valued for construction in medieval Cairo. But if we follow the traditional theory that these stones were directly quarried from the pyramid, we must imagine workers in the 14th and 15th centuries scaling hundreds of feet up the pyramid's steep sides, prying loose multi-ton stones with basic tools, and then maneuvering them carefully down to the ground without damaging their surfaces. Not only would this have been an incredible logistical challenge, but it also seems improbable given the technology of the time. Now contrast that with a more plausible scenario: stones that had already been blown off and scattered around the pyramid, resting in the desert sands. Picking up these stones and transporting them for reuse is still labor-intensive, but it's a lateral move. It is far more practical than carefully extracting stones from the pyramid's towering heights. Our theory of a solar-induced electrical discharge explains why these stones would have already been on the ground, detached and ready to be collected, simplifying the task of repurposing them for construction in Cairo. The idea that quarrying primarily involved collecting already fallen stones fits far better with the known limitations of 15th century technology. Second, let's delve into the cultural implications. The traditional theory requires us to believe that Egyptians, who revered the pyramids as sacred monuments, would have orchestrated an organized, large-scale defacement of one of the greatest architectural achievements in human history. This idea is unprecedented. To intentionally strip the pyramid of its beauty would have gone against the cultural and religious values of the time, especially when considering the pyramid's status as symbols of the divine and eternal. On the other hand, our theory suggests that the Egyptians did not actively desecrate the pyramid, but rather beautified the desert surrounding it. After a catastrophic solar-induced event scattered casing stones across the sands, the Egyptians likely saw an opportunity. In reusing these stones, they were not defacing the pyramid, but rather honoring its materials by incorporating them into new constructions, allowing them to continue serving a purpose. This interpretation aligns far more closely with the Egyptian cultural reverence for the pyramids and their symbolic power. So what does this mean for our understanding of the Great Pyramid? It suggests that the pyramid's missing casing stones were not the result of human greed or natural disaster alone, but were part of a far more complex interaction between ancient engineering, natural forces, and cultural values. Our theory of a solar-induced electrical discharge accounts for the selective stone loss, explains why stones ended up scattered in the surrounding desert, and aligns with the technological and cultural context of the time. In the end, the Great Pyramid may not just be a victim of history, but a participant in it, interacting with the Earth's natural forces in ways we are only beginning to understand. And as we continue to study this monument, we open the door to new perspectives on how the ancients perceived and harnessed the power of their world. The story of the missing casing stones is more than a tale of destruction. It is a testament to the enduring relationship between humanity, nature, and the cosmos. And in reimagining this story, we come closer to honoring the pyramid not only as a marvel of human ingenuity, but also as a witness to the powerful forces that have shaped our shared history.